So these are the review problems for Chapter 6. So let's see what we start with. Let's see, number 33. So 33 is one of the simple cases. You could say it's separation of variables, but it's probably even simpler than that. So we have dy dx is equal to x squared plus 3 over x. So because we're using separation of variables, we multiply both sides by dx. So you get dy is equal to the term on the left-hand side, right-hand side. But let's go ahead and simplify that. It's going to be x plus 3 over x. X squared divided by x is x. 3 over x is 3 over x. Multiply by dx. Integrate both sides. And then we just integrate. Well, the integral of dy is just y. And then we have the polynomial, so the integral of x is x squared over 2. Then we'll have this, which will be actually the natural log, because you have dx over x, 3, so we'll have the constant 3. Then the integral of dx over x is the natural log, the absolute value of x. And then we add our arbitrary constant c. And so this is should be the solution. So let me just check the answer in the book. 33. X squared over 2 plus 3, natural log of absolute value of x plus c. This is problem number 35 for the review, which is also one of these separable differential equations. So we have y prime minus 2xy is equal to 0. You could also solve this using integrating factors, but we don't need to. So what I would do is I would add 2xy to both sides. I would change y prime into dy dx. I would divide by y and multiply by dx. So I'd get dy over y is equal to 2x dx. Then I integrate both sides. And the integral of dy over y is the natural log of the absolute value of y. The integral of 2x dx, the integral of x is x squared over 2. And we have our arbitrary constant. These cancel out. But we can go ahead and raise both sides. Pardon me. We can have the exponent be both sides of the equation. So we can solve for natural log. So you solve for y. So you get, well, when we do e to the natural log of y, it just becomes y. Here we have e to the x squared times e to the c, but e to the c is just a constant itself, so we can just call that c. So we end up with y is equal to c e to the x squared. dy dx is equal to x squared plus y squared over 2xy. Well, if you try to separate this, you find that you can't do it. And it has that form of the homogeneous equation, because usually it ends up being a dy dx is some ratio of x and y's. And you can see that if I substitute it in, the rule is that if you substitute in for, so instead of f of x, y in this case, we'll say y prime is a function of x and y, you would get, well, f of x, y would be this thing. So you put an n or something in there, some constant times both of the terms. So you get nx squared plus ny squared by substituting in for x and y. You get 2 times nx times ny. And those are products. So we can change the order and group them appropriately, but you can see we get n squared and n squared, so we could factor that out. And in the denominator we have n times n, so we get n squared times 2 and then times x times y, and you can see that the squares cancel out, and you just get the original equation in this case. Now you don't have to get the original equation, you just have to get the original equation times some n to some power. In this case it's n to the 0 power. So that proves that it's homogeneous. So once we do that, then we can make the substitutions. The two substitutions are that y is equal to sum of v times x, and also if you take the derivative of that, you get dy is equal to v dx plus x dv. It's the product. First times the derivative of the second plus the second times the derivative of the first. So these are the two substitutions you make into this equation over here. And before we do that, though, let's go ahead and cross multiply just to get everything on the same level. So I've multiplied by 2xy, gets that over there, multiplied by dx, moves that over there, and now you can see everything's at a nice level. So now we make the substitutions. So for y we put in v times x. For dy we put in v dx plus x dv. On the right hand side, x squared just becomes, x just stays the same. You get y squared, y is vx squared, whole thing times dx. So dy gets substituted for and y gets substituted for. Okay, then you multiply all this stuff out. So we have 2x times vx times v dx. So it's all three of these, give us one term. So you get 2, how many x's do we have? 2 x's, so we get x squared. We have 2 v's, so we have v squared times dx. So that's this whole part. And then we have the second part, which is going to be 2 times x squared again, but we actually have x cubed, 2x cubed, x times x is x cubed. You get v from here, and then we get a dv. So that's the left-hand side. Right-hand side, what do we have? Well, we have x squared times dx. And then we also get v squared x squared times dx. So this is x squared, this is v squared x squared. Okay, once you multiply it all out, so let's write that in there, multiply out completely. We look at all the terms, look for a common factor, which we've got x squared, we've got x cubed, we've got x squared, we've got x squared. So, here we have x squared, basically x squared times x. So if we divide everything by x squared, what do we get? We get 2v squared dx plus 2x v dv is equal to dx plus v squared dx. Okay, the next thing you do is you combine like terms or try to get everything together, and you see we have a 2v squared dx here and a v squared dx here. So if I subtract, in this case I'm going to subtract v squared dx from both sides. That'll reduce the number of terms I have. So I'll have, well, 2 minus 1 is 1, so I get v squared dx plus 2x v dv is equal to dx. Okay, let's move everything involving dx to the right-hand side, everything involving dv to the other side. So we get 2x v dv is equal to dx minus v squared dx. So then you could factor out the dx out of this expression, because we have we have it in both cases. So you get 1 minus v squared dx. And now we can separate variables. So we divide by this and we divide by that. So that will leave us v dv divided by 1 minus v squared is equal to dx over 2x. Now this is about as far as I usually am going to ask you to do in the test. But we're going to go ahead and finish it off just to show you how it works. So actually, what we're going to do is we are going to multiply by 2. So we're going to have 2v dv over 1 minus v squared is equal to dx over x. And then you integrate both sides of that, just like we do a normal separation of variables. So when you integrate this, okay, this one's going to be the natural log of x. That's the value of x. We'll add our arbitrary constant c. Over here, if we let u equal the denominator, 1 minus v squared, so we're using u substitution, du is, this goes to 0, you get negative 2v dv. And what we have was 2v dv. So 2v dv is equal to negative du. So we can make that substitution there, and we can use that substitution there. And so this becomes the integral of negative du over u. So the integral of negative du over u is equal to negative the natural log of the absolute value of u is equal to the natural log of the absolute value of x plus c. Substitute u back in, so you got two substitutions here. One that's a u substitution to the integration, one that's this other substitution to make it homogeneous. So that goes in there, so you get negative the natural log of the absolute value of 1 minus v squared is equal to the natural log of the absolute value of x plus c. And then if you just wanted to solve for, if you remember v, well, y is equal to v times x, so v is equal to y over x. Divide both sides by x. Get that. So then we could say minus the natural log, the absolute value of 1 minus the quantity y over x, quantity squared. So that's v squared is equal to the natural log, the absolute value of x plus c. So that would be as far as we could let things go. But you know, there are other things you can do here. What we're going to actually do is do this, and okay, I think we're just going to leave it there. There are some ways you can simplify it. You change this to the natural log of a constant, combine those two, or combine these two, and then you would move that inside so that you'd have 1 over this quantity, and then you would do e to both sides, and you could solve for it. But I think that's far enough for right now. Okay, so that's it. Okay, what do we have next here? 43. 43 is a logistic growth problem. P of t is equal to 7,200, which is our carrying capacity, 1 plus 44 e to the minus 0.55 t. Okay, so it's asking a couple questions. Use it to find the value of k. Well, k, part A, k is always the constant here, so it's 0.55. Just getting this problem. So, okay. L, the carrying capacity is L, which is this number at top. So L is equal to 7,200. C. Find the initial population. Well, That's when t equals 0. So P of 0 is 7,200 divided by 1 plus 44 e to the 0. Because when you t equals 0, 0 times that is 0, e to the 0 is 1. So it's just going to be equal to 7,200 divided by 1 plus 44, or 7,200 divided by 45. So if we get our calculator out, 7,200 divided by 45 is 160. So that's the initial condition, P of 0. It's easily, you just take this number divided by that, 1 plus whatever B is, that constant. Okay, determine when the population will reach 50% of its carrying capacity. So that means P of t divided by P0 is equal to 0.5. So that's, well, no. Initial comparing capacity, sorry, that's wrong. I was thinking of the half-life. So it's saying P of t equals 3,600 because the carrying capacity is 7,200. So we just plug that in and solve for t. So we have 3,600 is equal to 7,200 divided by 1 plus 44 e to the minus 0.55 times t, and we solve for t. So what we can do, kind of as a quick thing, is we can just switch the numerators and the denominators for the two sides. So this goes up there and that goes down there. So you get 7,200 divided by 3,600, which is 2. So you get 1 plus 44 e to the minus 0.55 t is equal to 2. So you subtract 1 from both sides. 44 e to the minus 0.55 t is equal to 1. Then you divide by 44 on both sides, so you get 1 over 44. Yeah, so what do you do now? Well, you take the natural log of both sides. So the natural log of e to the negative 0.55 t is equal to the natural log of 1 over 44. And the natural log of 1 over 44 should be a negative number because it's between 0 and 1. So you get the natural log of 1 divided by 44 is negative 3.78. And on the left-hand side, you just have the exponent. So then to solve for our unknown t, just divide by the constant, or k, which is negative 0.55. So t is negative 3.78 divided by negative 0.55, and that's 6.9. And what are the units? Does it say? 6.9 units, whatever they are. It's 43. 6.88. Yep, okay. And then the final one says, write a logistic differential equation that has a solution. So the logistic differential equation is a solution of the differential equation where this is the carrying capacity and this is the K, and the 44 comes from the initial condition. So what we would do is we would say dP dt is equal to K times T 1 minus P, which is the variable, divided by the carrying capacity, which is 7,200. And we could also say that, you know, P of 0 is equal to 160. With that, you get this 44 if you actually did it. So that's the differential equation: K T times 1 minus P over. No, it's not T. It's P. So this is P. Okay, so Kp times 1 minus P over L. Done. Now we're moving on to first order differential equations, which means that we use the integrating factor approach. So we get y prime minus y is equal to 8. Okay, I'm not going to write it down, but I'm going to tell you what the steps are. Put in standard form, check. P of x, it's always what's in front of there, so in this case it's just -1. Calculate the integrating factor using this formula. U of x is equal to e to the integral of p of x dx. So we plug in p of x into our little integral. So we get negative dx. P of x is -1. -1 times dx is negative dx. So the integral of that is going to be e to the minus x. The integral of dx is x. So that's it. Can't use the properties of natural logs because there's no natural log involved. That would only happens when you have dx over x in here. Once you have the integrating factor, you multiply the equation by that integrating factor. So it's every term. This times those two terms is just going to become the integrating factor times the variable y. The whole thing primed, which means that this plus this times that results in a product rule that can be collapsed. Then we multiply this times the right-hand side, which is 8e to the minus x. Then you integrate both sides. Well, the integral of the left-hand side just becomes the expression in the parentheses, and then we integrate the right-hand side, having multiplied by dx, so we can get a nice integral. So the integral of e to the minus x is going to be, notice I just brought the constant out, is actually going to be negative e to the minus x dx, not dx. And then we add our arbitrary constant c. So the left-hand side just stays the same, and then we get the integral. Remember, the integral of e to dx is e to dx. The integral of e to the minus x is minus e to the minus x. That's because if you let u equal negative x, then dx is negative dx. So when you make that substitution, you get negative du, and that's where the negative sign comes from. Solve for y. So we're going to multiply everything. We'll just show that. We're going to multiply everything by e to the x. That makes that disappear, or go to 1. E to the minus x times e to the x. You add the exponents. X minus x is 0, and e to the 0 is 1, so it just becomes y. So you get y is equal to, what happens here? Well, same thing happens. So you just get negative 8 plus c e to the x. And I would probably write that with c e to the x minus 8, just so the constant second, because it's negative. Okay, let me check, see if everything's okay. Negative 8 plus c e to the x. Okay, they just left it at that. So we're on problem 51, which is another integrating factor problem without initial conditions, which I'm not sure if we actually do one of those. Actually, I want to do 51. Not 50. Oh yeah, it is 51. Okay. 51. X minus 2, y prime plus y is equal to 1. Just put it in standard form. That means divide every term by x minus 2. So we get y prime plus 1 over x minus 2y is equal to 1 over x minus 2. Okay, standard form, p of x. What's p of x? 1 over x minus 2. So the integrating factor is e to the integral of p of x So that's going to be equal to e to the natural log the absolute value of x minus 2. Because we have, if you let u equal x minus 2, du is equal to dx. So you integrate that and you get the natural log of u, absolute value of u, substitute u back in, you get that. And we can use the inverse properties of logarithms and exponential functions there to rewrite that as just x minus 2. So that's the result. So what do we get? Well, then we take that and multiply it by the original equation, which becomes, I'm just thinking here, yes, okay. So we multiply that by the equation in standard form. Okay, so now what happens? Well, these two added together times that just becomes x minus 2 times y, the whole thing primed. Does that make sense? Well, if you take the derivative of this, you get the derivative of x, which is 1, so you get y prime. And I did something wrong. What the heck did I do wrong here? Did I do something wrong? Oh yeah, and this is just, if you multiply this out, you just get 1 here. So the derivative of this is the second part, and then you take that. Yeah, so it works out. Over here we get x minus 2 over x minus 2, which is just 1. Prime. Okay, now you integrate. When you integrate the left-hand side, it just becomes the integrating factor times y. Over here we get x, the integral of 1 is x, plus our arbitrary constant c. So the integral of 1 dx is x plus c. So now what do? Well, we divide by x minus 2, so you get y is equal to x divided by x minus 2 plus c divided by x minus 2, which is the same as x plus c over x minus 2, and that's the answer. Now, I don't know if you can solve this using separation of variables or not. I'm trying to think here. Yeah, I think so. And the final one is 55, which actually is not the final one. I'm going to add another one here, which is the Bernoulli equation problem. So this is the next to last one. I didn't assign it today, but I will assign it tomorrow. Standard form, check. P of x, u of x, so you get e to the 5x is the integral of 5 dx is 5x. Multiply this times the original differential equation. Okay, so this plus that times that becomes e to the 5x times y prime. The other side is e to the 5x times e to the 5x is e to the 10x. Yeah, the exponents. 5x plus 5x is 10x. So we integrate both sides. So the left-hand side just becomes e to the 5x times y. The right-hand side becomes the integral of e to the 10x dx. So we would let u equal 10x. du would be equal to 10 dx, or dx is equal to du divided by 10. So we do these two substitutions, and the right-hand side becomes the integral of du over 10 times e to the u. So you factor out the 10, which is in the denominator, and that leaves you with e to the u du, which we do know how to solve. And e to the u du integral is e to the u. So we get e to the 5xy is equal to 1/10 e to the u plus our arbitrary constant c. And then we substitute u back in. U is 10x, so we get e to the 10x plus c. Solve for y. So we can multiply this whole thing times e to the minus 5x, because e to the 5x times e to the minus 5x is 1, because you get e to the 0, which is 1, so that'll just leave you with y on the left-hand side. And then we subtract 5. 10 minus 5 is 5, so we get 1/10 e to the 5x plus c e to the negative 5x. And you could factor out, no, you can't do that. Is that the answer? 55. 1/10 e to the 5x plus c e to the minus 5x. That's it. So the last problem is 58, which is a Bernoulli equation. And at least for the test, you just have to be responsible for getting it in a form where you have an equation that's a first-order linear differential equation. In this case, it's not linear because I have this y squared term. So I multiply by y to the minus 2. So I get y to the minus 2 times y plus 2x times y to the minus 2 is equal to x times y squared times y to the minus 2. Okay, so here you get y to the 2 minus y to the minus 2, you get y to the 0, which is 1. So the right-hand side just becomes x. And let's just rewrite this with the positive exponents in the denominator. Now, y times y to the minus 2 is y to the minus 1, because this is the first power. 1 minus 2 is negative 1, so we get y to the minus 1, which is 1 over y. Okay, now, here's the point where you define your variable, which I guess we're calling v, or z. I don't know which one it is. Let's call it z. So z is equal to this term, 1 over y, which is equal to y to the minus 1 power again. So when I calculate z prime using implicit differentiation, remember implicit differentiation, got to do that, you get minus 1 y to the minus 2 times y prime. The negative comes from the exponent, negative 1. You decrease the exponent by 1 when you take the derivative, and you multiply by y prime because it's we're making the derivative with respect to x. So you have to have the implicit y prime on there. So we should be able to solve for this part. So let's rewrite this. Z prime is equal to negative y prime over y squared. I'm moving this from the numerator to the denominator, making it positive. And so y prime over y squared is equal to negative z prime. So just multiply both sides by negative 1. So now I can make the substitution. So you get negative z prime plus 2x z is equal to x. And if I divide by negative 1 or multiply by negative 1, I'll get z prime is equal to negative 2x z is equal to negative x. So this now is a first-order linear differential equation. This is as much as I'd ask you to do for the test, but I'm going to finish it off if you're interested. So what we do, once it's in standard form, we figure out what P of X is, calculate the integrating factor, and let me make sure I'm doing this right. Yep, I think so. Okay, so you get U of X is equal to e to the minus 2x squared. Negative 2 comes out, integral of x dx is x squared. So that's my integrating factor. So then I take that integrating factor and I multiply it by the original expression. Like that. This times those two terms can be collapsed into just the integrating factor times the variable, which is z in this case, not y. Over here we have negative x e to the minus 2x squared. So we integrate both sides. The integral here becomes just the terms, and the integral on the right-hand side is negative x e to the minus 2x squared. So I have to use u substitution in this right-hand side. So I'm going to say u, not u of x, but just u. U is equal to negative 2x squared, the exponent. So du becomes negative 4x dx. And what I need, I forgot a dx here. What I've got is negative x dx. So negative x dx is just equal to du divided by 4. If I divide both sides by 4, I get negative x dx. So then I can make those substitutions into here. And I would get the integral of e to the minus e to the u du divided by 4. Factor out the 4, so I'll have 1/4. The integral of e to the u is e to the u, and I'll add my arbitrary constant. And then what I would do is I substitute u back in, which was negative 2x squared. So I get e to the minus 2x squared. Z is equal to 1/4 e to the minus 2x squared plus c. And now I want to solve for z, so I take the whole thing and I multiply it by e to the positive 2x squared, which makes this go to 1 and makes me allow to solve for z. The same thing happens here, so I just get 1/4, and then I have c e to the 2x squared. And then finally I make the substitution back in. Z was equal to something, so I go back and look, and z was equal to, where was z equal to? 1 over y. So I substitute that in, I get 1 over y is equal to 1/4 plus c e to the 2x, which is 1 over y is equal to, what do we have? So if I multiply by 4, this by 4, I will get 1 plus 4c e to the 2x over 4. Found a common denominator of 4. So if I multiply both the numerator and the denominator by 4, this becomes 1, which cancels. Okay, so now you can just take the reciprocal, and so you get 4 divided by 1 plus 4 c e to the 2x, and I've got 4 times c, so because that always comes out through the initial condition, I can just rewrite that as just c to make it simpler. Kind of looks like the logistic growth equation to some extent. Anyway, that was 58, and I'm just checking to see if I did something wrong or right. It seemed to be off. Got an extra 2 in there somehow or another. get that extra 2. Okay, they have e to the x squared. Where did I gonna get 2x squared? Oh, yeah, there it is. So that's what happens. So this just becomes x squared, negative x squared, which is negative 2x dx. So anyway, that's where my error was. So anyway, there you go.